This tutorial is exercise 8 and it's the MMC external feature. To start off, open up the exercise 8 MMC external PDF file. So what we're going to be doing in this tutorial is we're going to look at the MMC condition with an external feature, which is a shaft. We're going to look at the virtual condition and the resultant condition, and we're going to be calculating our outer and inner boundaries. Now if we look at the flowchart, the virtual condition, the external shaft feature is going to be MMC, it's a constant value, and it's going to be our outer boundary. With the resultant condition, we're again going to have the shaft, MMC, a variable value, and in this case it's going to be our inner boundary. Now we have our formulas for the external feature. So with the virtual condition, it's the MMC plus the tolerance. For the variable, it's the variable feature minus the variable tolerance. Now again we have our part. So our part is a shaft coming out that's 24.5 to 24.9, and we are going to have a tolerance of 0.1 at maximum material condition for the positioning. Now what we're going to do is the same as the last one. We're going to start with the feature size. We're going to fill in the table, and we're going to be able to find our virtual and resultant conditions, our inner and outer bounds, so that we're able to create our components. So 24.9, 24.8, 24.7, 24.6, and 24.5. So we have our parts there. Now we have to look at our condition. Which one is the maximum material condition? With the shaft, it's the one with the largest feature, so it's going to be MMC for this feature here. The tolerance is going to be 0.10. We'll look at our formula, and the virtual condition is going to be the MMC feature plus the tolerance. So that makes our virtual condition 25. Now again, we're going to have to fill in the tolerances here, and the tolerance again is going to vary with the part, and we always want the feature plus the tolerance to equal the virtual condition. So in this case our tolerance is going to be increasing here, so 0.20, 0.3, 0.4, and 0.5, and that creates all of our tolerances. Now if you remember from the previous one that we did, it was the smallest feature had the smallest tolerance, and the greatest feature had the greatest tolerance. In this case it goes in reverse order, and that's because the virtual condition is the outer bounds. And I'm just going to show you another example of why that is. If we think of the shaded area as the virtual condition, so that's the outer bounds, and we think of these two circles as two different sizes, for the large circle to stay within the virtual condition, it can't move. Its tolerance is limited, so it can't move too much. If we look at the small circle, it has a large tolerance. It's able to move around a lot, so it has a lot more degree of freedom to move around compared to the large one. And that's why with the shaft having the outer bounds being our virtual condition, the tolerance is going to be the greatest for a small peg location, and it's going to be the smallest for a large peg location. So now we'll finish off by calculating our resultant, and in this case the resultant is the variable feature size minus the variable tolerance, and this is going to be our inner bounds. So let's start calculating this. This is going to be 24.8, 24.6, 24.4, 24.2, and 24. So from the GD&T that we've created for this shaft, we've got our virtual and resultant condition, and from these we have our inner and outer bounds. So our outer bounds for the part is 25, and our inner bounds is 24. So from the part, the GD&T, and doing the maximum material condition, we've created our inner and outer bounds for creating our parts and assemblies. And that concludes our tutorial.